Thanks. Beginning with a word of prayer. Dear Heavenly Father, we thank you for this day. Again, thank you for these students. Just pray to be with us today. Help us to just draw together our thoughts about Chapter 3 in Gamelin. And again, Lord, I thank you for these students. In my prayer, Lord Jesus. Amen. Okay, so talk about harmonic conjugates. So we're roughly speaking in section 3.3. And here's the lemma we'll begin with. Oh, just let me remind you, and I'm not sure I made this a formal definition before, but let me just make it now if I haven't already. If you have f is equal to u plus iv, then f is harmonic on some domain D. What that means is that u and v are harmonic on D, which means that, of course, uxx plus uyy equals to 0, and vxx plus vyy equals to 0. All right? So that's what harmonic means for us. And so here's a lemma. 3.31. If u is harmonic, then the differential, and here it is, let me call it omega. Omega equals to, I'm just calling it omega to give myself something, just a name to call it, right? So partial u partial y dx plus partial u partial x dy is, here's the punchline, closed. All right. So how did we, let's see here, so that's the claim. So what do we need to do then? Assume u is a harmonic, right? And then consider omega as above. So if we say omega is equal to p dx plus q dy, what do we have? This marker is dead to me. Stupid lid. What do we need? We wish to show what? We wish to show that partial x of q is equal to partial y of p, right? Identify, I'm assuming that omega is this particular differential form built from partial derivatives of the given u. So we've got what? We've got p is equal to minus partial u partial y, and we've got q is equal to partial u partial x, right? So what do we get then? Partial xq is partial x of partial u partial x, right? Which is uxx. And what else do we have? Partial y of p, what's that equal to in this case? It's partial y of, well, my p, the x coefficient is minus partial u partial y. All right? So that gives me minus uyy. But hey, u is harmonic, so what does that mean? uxx plus uyy is equal to 0, right? So this is equal to uxx. So therefore, omega is closed. So what does that tell us? If it's closed, right? If it's closed and we're on a star-shaped domain, that means that this form omega is also path-independent, integrals around loops are 0, and it's also exact, right? If we have in addition that topological criteria of star-shaped domain, right? All right, so there's perhaps an unexpected connection. I don't know. What do you think? So let's continue this discussion here. So if we have, what do we know? Our previous section, we already proved that if D is a star-shaped domain, then it's exact, right? So like from last class or the class before, from previous work, if D is star-shaped, right? And so, U is harmonic, so that, by the lemma, what do we have? Yeah, this corresponding form, minus partial U, partial Y, dx, plus partial U, partial X, dy, so that this is closed. So if this is closed, and it's a star-shaped domain, what does that tell us also? Not that it equals 0, it equals the total, it's the total differential of some potential function, right? We built that potential function from integration, remember? So we can say that this is equal to, now this, this kind of, I guess I could, maybe using v here kind of, maybe logically is not quite, it's a question notation. I'll just say it's dv though. That's for my own self-serving purposes though, logically speaking, as you'll see shortly. This is what? This is partial v partial x dx plus partial v partial y dy, right? So what does that tell us about the relation between the potential function v and the given harmonic function u? So you look at this, and what do we get? We get minus uy is equal to vx from the x coefficient, from equating these two, right? And then from equating the dy coefficients, we get partial ux is equal to vy. What are those? Yeah, those are the Cauchy-Riemann equations. So what's that tell us? These are the Cauchy-Riemann equations, and these hold in a domain, right? In D, a domain. In fact, a star-shaped domain, right? So that suffices to tell us what about f equals to u plus iv. What's that? Say again? Complex differentiable on the whole domain, right? So it's holomorphic on D. Now, by the way, just a small point. How do I know I can equate coefficients of differentials? Like, how should you understand a differential form? What is it actually a shorthand for in our current way of thinking? It's really a shorthand for expressions of integrals, right? So being able to equate those two forms in some sense, it's a statement about a whole family of line integrals. So of course you can take integrals of the right shape in order to just pick off the dx term or just pick off the dy term by just picking horizontal lines and vertical lines. So it's not crazy to equate these coefficients at all, even in our current understanding of differential forms, which is that really it's just a shorthand for some line integral that we're doing. Okay. They do take a life of their own as you go on, but not quite yet. All right. Any questions? So the theorem we have just proved is theorem 3.32, which says that if u is harmonic on a star-shaped domain, then there exists a function v such that u plus iv is holomorphic. All right, so that's what we've shown. If you have harmonic on a star-shaped domain, then you can find a harmonic conjugate. All right. Now, let's see. The example Gamelin gives of this is he finds the harmonic conjugate of the log of the modulus of z. So let me see if I can work through that. Now, see how that goes. I'll give it a try. Give it a shot here. So here's a reminder. Our proof, remember our proof that closed is exact? What did we do? How did we build the v? Something like this, right? V of b was equal to the integral from a to b of, well, in our current context, minus partial u partial x dx, dy, rather. Wait a minute. Oh, sorry. By the way, to me, this is very, these expressions in some sense are very unnatural. We will later learn better notation to understand where these are coming from. So at the moment, I mean, it is where we are, so I have to deal with it, but let me not say more. It's hard for me to remember this sometimes. Okay, so sorry, I'm trying to behave. It's taking me a moment to summon my courage to behave, and not say things I shouldn't say. All right.
Did you just say the things?
No. Do not tempt me. No, I'm not trying to use 7 as a variable. So this is a template for building V, like we did in the proof that closed implied exact, right, on a star-shaped domain. We proved that last time. Remember? Looked at the little triangle, applied Green's theorem, all that. So let's apply this to an example. Let's try it. So suppose you have u is equal to the log of the modulus of z on for d equals to c minus. That, as we've explained before, is star-shaped, right? So goodness gracious, I guess I should probably say principal log, huh? Let's be specific. All right. Is this harmonic? Well, if we're going to check directly, I mean, a baby. Let's see here. So this is u is equal to 1/2 how to say this? I mean, that's real, right? So u is just 1/2 natural log of x squared plus y squared, right? Unless I'm overlooking something. I don't think so. I mean, the modulus of z is real. So the complex logarithm just breaks back down to the regular logarithm. And square root pulls out to 1/2. And so you can easily calculate ux as what? X over x squared plus y squared, right? So what's uxx? Man, we almost did this differentiation last class. That's funny. Maybe we did this differentiation last class. It's quotient rule, right? So we get what? We get x squared plus y squared minus 2x, yeah? Over x squared plus y squared squared. So we get what? We've got, I think I've lost my, what did I lose? I lost my x. There's an x here, right? Dos Equis. So we've got y squared. I really want one of those cutouts. Let's see here, x squared plus y squared squared. Sorry, the baby's disturbing me. And by symmetry, uyy is equal to x squared minus y squared over x squared plus y squared squared, right? X and y appear symmetrically in the formula for u, so the derivative will be the same, just switching the roles of x and y. And then you can clearly see that, therefore, uxx plus uyy is equal to 0, right? Yes, sir?
So does the Cauchy-Riemann equations being correct imply that the function is harmonic, and does the function being harmonic imply that the Cauchy-Riemann equations are satisfied?
One question at a time. So first of all, if the function is complex different, what did you say?
If the CR equations are satisfied,
yeah,
does that imply that the function that u and f equals u plus iv is harmonic?
Yes.
Okay, and does f being harmonic imply that the Cauchy-Riemann equations hold?
Hmm. Mm. I'm not sure right off the top of my head, honestly, Michael. Anybody have an idea? So his question is, does harmonic imply, so harmonic, I mean, now you gotta be more specific though. Do you mean harmonic on a domain? Let's say. So you have U and V harmonic on a domain. Does that imply then that U plus IV is holomorphic? Right?
Yes.
Yes, it does.
Okay.
That was what we proved. Yeah. Sorry, I forget.
No problem.
I mean, we proved it 5 minutes ago. I should remember. I mean, you not remembering is fine. It's your prerogative. You're a student. I just taught you that. Sadness. Anyway, so this is harmonic, right? So if we believe what we did last time applies to specific examples, then we should be able to calculate the harmonic conjugate using this integration process, right? So what is the slit complex plane? I always draw it as a square with a deleted sort of a square Pac-Man. Of course, it goes on and on. This is just a stupid picture that helps me think about it. I got to pick some kind of reference point for the setup of the integral. What should I use? I mean, all things being considered, I'll use the number 1 as A. You got to pick some reference point for your potential, basically.
You should use 2 as b then.
B is a variable, though, so I want to figure out, what is this? So I need to calculate then for, v of b would be the integral from 1 to b of partial u. Now this thing right here, right? So what is partial u partial x? So I've got partial u partial x dy minus partial u partial y dx, or vice versa. So partial u partial y would be, what would it be? It would be, so I've got like minus y dx plus x dy all over x squared plus y squared, right? Does that look familiar? Isn't this the one I showed last class is not exact? Remember, we took that form, that exact expression, and I integrated this around the unit circle, and I got 2 pi. Remember? Why is that appearing here? What's that? Because it's star-shaped. Yeah, I mean, let me just cut through the nonsense here. Basically, you can look at this as the integral from 1 to b. And another way to write this, right, would be that this is just the differential of theta, where theta is equal to inverse tangent of y over x. If you calculate the differential of this, the differential of the inverse tangent function, you get that. Now, admittedly, there I've made a further specialization of the domain, assuming that theta can actually be expressed as that, right? So, I mean, all right, fine. I'm now limiting myself to the quadrants 1 and 4, right? Where this makes sense between minus 90 and 90 degrees, right? So what is this then? This just is this theta of b minus theta of 1, right? By the way, if you, trying to think of how to say this, but, well, I mean, that's pretty much it. I mean, that's, The point here is that the harmonic conjugate v is really just the argument. Well, the right branch of the argument to make sense. Does that make sense, by the way? What is this? So in other words, v, I mean, let me not eat all of class on this, but basically what we're beginning to see the start of is a careful argument that v is equal to the argument. I haven't quite fleshed this out yet, but v is the argument of z. And so then I have what? I've got f is equal to u plus iv, which is what? The natural log, listen to me, log, principal log of the modulus of z plus I times the arg of z. What is that? You should recognize this is, in fact, just the logarithm of z, the principal logarithm. That's the principal logarithm of the modulus, which is the real component. Oh, you know what? It occurs to me now, when he uses little log here, he may actually mean natural log at the start of this problem, right? I could have, without changing anything here, you notice basically at the start here, I could have crossed this out and in our notation put little ln, and it would have been, maybe, I mean, it's not wrong what we wrote, it's just maybe philosophically that's better. Natural log of that. As you can see, that's the principal log, right? It's probably kind of bad form to define the principal logarithm in terms of the principal logarithm, which is kind of what I was advocating with my previous expression. Like I've got log of z is equal to big log of the modulus of z plus I arg. I mean, that's not how you define something, right? You should define the principal logarithm in terms of other things that you know. In this case, natural log and the argument. Anyway, do you see? So now, if I had asked you on the test, right? There's different. I mean, you already this could have been a test question, right? But how would you have done it on the test? You'd have tried to solve the Cauchy-Riemann equations directly, right? Or you would have tried to guess. You'd have been like, well, I know that if u is equal to the natural log of the modulus of z, then that's the real component. That's just the real component of this complex differentiable function log z. So I say, okay, well, that's holomorphic, and I know that the component functions, the real and imaginary parts, are themselves harmonic, so I don't need to do all this. I can just be like, okay, well, this is holomorphic, so its component functions are harmonic, basically by guessing that this is the corresponding complex function to that harmonic function. But you don't have to guess, right? You could follow through this integration process. But it can the detail can kind of be a hassle. I cheated a little bit here by identifying that as d theta and using a geometric argument. It can be made precise if you're willing to put in another half hour of class time on it. I will not do that. That brings us to section 3.4. Oh, so just to recap, we can talk about differential forms of the complex, right? And we have what different characterizations do we have? We've got exact, we've got closed, path independent, right? Integral around loop is 0. If the form is closed, then we can between two paths, then we can deform the integral from one path to the other, right? And do you now understand why it is that we couldn't? Why, even though so just I'll make sure you guys get the point here. So we had omega is equal to minus y dx, right? Plus x dy over x squared plus y squared. So basically what I'm telling you is the way to understand this quickly is that this is d theta, right? So the reason that when we integrated omega over the unit circle gamma, we got 2 pi is because we were integrating the differential of the angle function. With the understanding, of course, the angle function, I mean, really, I could perhaps write this more specifically as d little arg of z in some sense, right? Where you could choose different branches depending on what you're doing. Now, the example, so I mean, the point is you can't go all the way around the circle and have the same argument. Because why? If you had the argument go all the way around the complex plane, encircling the origin all the way around, what has to happen is you have to have that 2 pi angle jump. Well, that's not continuous, right? Continuity is a necessary requirement if you're going to take the derivative of it. So that's an inevitable breakdown. You have to throw out a ray somewhere, and that's where the 2 pi comes from, which was the point of that homework problem I gave you guys, to see the jump in the logarithms argument as you go around the circle. That's related. Anyway. So, definition. Sorry, guys, you guys make me nervous when you don't say anything. Believe it or not. Oh, hi.
Okay, I have a question then.
Uh-oh. What have I done? Yes, go on, Michael.
Why is negative y dx plus x dy over x squared plus y squared equal to d theta?
Oh, you just have to, if you take the partial derivatives of this with respect to x and y, out pops that.
Okay.
It's just a little calculation. It just like stone cold calculate the total differential of inverse tangent of y over x. And you'd be like, well, that's only good in quadrants 1 and 4. Well, fine. You know, the standard angle in the other quadrants are just related to this by a shift. So you just add a constant to get the standard angle in the other in the other quadrants. So if the derivative works out to what it works out to in quadrants 1 and 4, it's just the same in the other two quadrants.
You are putting words in my mouth. I never complained.
Oh, okay. I think it was.
I understand now. That makes sense.
Okay.
Thank you for saying that.
Oh, you're welcome. Okay, so if we have h going from d to r, a continuous function on a domain D, and let z naught be an element of D such that the disk here it is, z in the complexes such that the modulus of z minus z naught is less than rho. In other words, this, by the way, is the disk of radius rho centered at z naught in my usual notation. That's a subset of D. Then the average value of h of z on the circle if you let me just be lazy, I'm going to say the circle is the boundary of this. In other words, take this inequality and make it equality. That's the circle, right? So the average value on the boundary circle to that disk is given by a of r is equal to integral from 0 to 2 pi h. Oh, I'm sorry, I messed it up. It's not for that circle. It's for an arbitrary, stupid circle. Fine. Z and C. I thought I'd save myself some writing. Obviously, I failed. Z naught equals to r. So the circle of radius r, centered at z naught. So you do h of z naught plus r e to the I theta d theta over 2 pi. All right. So this is the so-called average value. Now, on the circle of radius r. So that's what the r dependence here is, the average over a circle of radius r, right? Now, how would you define the average? I personally, when I think of defining an average for a function of several variables, I usually think about doing some kind of integration over the region in question and then dividing by like the volume of the region, whatever that would be. In this case, to me, the volume of the circle would be the length of the circle, right? So my intuitive definition of average here would just be, take the function h and integrate it around the parameterization of the circle, right? And then divide by the circumference of the circle, right? Which isn't quite what he writes there, is it? But if you work through it, in fact, that's just a different formula for what I described. It's really just taking the weighted average of the values of the circle divided by the arc length. It's just that, he changes to d theta. What's the relation between arc length and what's the relation? ds, right, is equal to r d theta, right, on the circle. So if he trades a ds for a d theta, he picks up an r, and then the r, which would be down here, cancels out. And so that's why this is the same as taking the average over arc length. Anyway, so that's the definition. You're like, well, that, this kind of, to me, if I was a student, I'd be like, what on earth are we what happened here? Why are we talking about this? Isn't this kind of a bizarre jumping off? What's the connection between what we're doing right now and what we were doing? I hope so. Theorem. If U is harmonic on a domain D, and if the disk lost my place, modulus of z minus z naught. So the disk of radius rho is contained in D. All right, then U of z naught is equal to the integral from 0 to 2 pi of U of z naught plus r e to the I theta d theta over 2 pi for 0 less than r less than rho. So here's a picture. Here's D. Here's the disk radius rho, right? And we're saying you can run the average on any circle in here of radius r like that. So for any r between 0 and rho, the center here is z naught, right? What does it say in words?
That the functional value at z0 is equal to the average value.
Mm-hmm. It says the average, so it says the value of a harmonic function at the center of the circle is equal to the average of its values on the circle. And that's true for any circle around that point. Well, within the rho, right? Here's the proof. I think this is an interesting proof. So it's harmonic, right? Implies closed, right? And that implies that the integral around a loop is 0, right? In particular, which integral around a loop? Well, the integral around, let's see, the loop I'm talking about, of course, is the circle of radius r. And we'll orient it counterclockwise, as usual. So this is notation for the integral around the circle of radius r centered at z naught, counterclockwise. You see the notation? Yeah? In which form? Well, the one we've been looking at earlier today, minus partial u, partial y dx, plus partial u, partial x dy. Okay? Now, so if we put this into detail, so what is how do you do this integral? You put what? Z equals to what? z naught e to the I theta, right? I'm sorry, what do you say? Oh. Well, I mean z naught plus, I should say, r e to the I theta, right? In other words, x is equal to x naught plus r cosine theta, and y is equal to y naught plus r sine theta. That's the details of the parameterization. So when you calculate dx, what do you get? So we can integrate from 0 to 2 pi minus partial u, partial y, and the dx is what? It's r is a constant here, right? So minus r sine theta d theta plus partial u, partial x. The dy is what is it? It's r cosine theta d theta. Yeah.
Why does z equal what it does?
That's the parameterization of a circle of radius r. So what is that, though? And then here's a kind of sneaky thing. So I can pull the r out, right? If you don't mind, I'm going to go ahead and do that. Pull this r out, right? So I've got r, integral from 0 to 2 pi. And then what do I have here? Partial u, partial y. And so what would be left would be sine theta. So think about this. Sine theta is also partial y, partial r. Because if y is equal to r sine theta, right, plus y naught, so partial y, partial r is sine theta, right? And over here, you've got partial u, partial x. There's a cosine theta left. Well, what's cosine theta?
Partial x, partial r.
Yeah, partial x, partial r. So, chain rule says that this is really partial partial r of what? Of u, right? Now, technically, it's u evaluated at the parameterization in order to make the chain rule flesh out, right? But let me not be too explicit. So then, we use a trick of advanced calculus or analysis, or perhaps neither. But in principle, there might exist a class where you'd prove this in the sense that you can pull this derivative outside of the integral. And to be more specific, this is u of what? It's u of z naught plus r e to the I theta, to be explicit. That was the dependence. Fine. This is u of z naught plus r e to the I theta in the step before. I mean, that's the derivative of this gives you that with the identifications we've made. Now, you can switch the order of integration and differentiation, provided you have sufficient, let's say, conditions on the thing you're integrating. You need some sort of like uniform continuity of some sort or another. Now here we're assuming u is smooth, and this is a finite integral, so it's probably harmless. But anyway, there's a jump there. Okay. But I've used a theorem of analysis there that you can switch the integral and the derivative like so. And once you do that, what do you have? We have, so if I divide this by, divide by 2 pi r, right? I get 0 is equal to partial partial r of the integral from 0 to 2 pi of what? U of, you see what that is? which is the average value, yes. So we have just showed that the average value, partial A, partial R, I mean, you could make this a dA dr, right? I think technically when I pull the derivative outside the integral, I probably should change this to a ddr because it's no longer a function of two variables, but that's just semantics. So anyway, this does imply, of course, that the total derivative of A with respect to R is equal to 0, which then says what about A? Now, how do I know it implies it's constant? What did I assume about the domain? I assumed it's a domain. What does a domain mean? Domain is a technical term in here, right? It has theoretical content. What is it?
It's connected and
Mm-hmm. That's it. It's connected and open. So region is the word we use for connected, but possibly not open. So like region would be a domain plus some of its boundary points, perhaps. But a domain is an open connected set. And if you have a function that's why I know that this is constant, is because I have the derivative vanishes on an open connected set. As we proved before, that means it's constant, right? Okay, so how do you know what the constant is? Then there's like there's a little argument that I have. Well, let me put it up on the projector. I don't want to write it out. Basically, you can argue that the value has to be. You can show that you can find the value of the constant by making a little continuity argument here, based on a simple little estimation that's in Gamelin. Let me show you. Come on. Wake up. Oh, please no. We had trouble in advanced yesterday. The projector was all very yellow. Which is weird because apparently Dr. Wang was using it right before me with good success. I'm sorry. I love this. I love this misspelling. It brings me joy. All right, sorry. It made me think about, in my own work, how could I use angel as a technical term?
You did that one time when you were helping me.
I did? Oh, I probably would misspell it. It's definitely something I would misspell and get made fun of. That's true. That is true. I wouldn't take that away from you. Let's see here.
Kind of people at Liberty.
Oh, have fun with me then. Unsolicited fun. Let's see here. Where were we? Where were we? Ah, yes. The mean value property. This definitely has to do with Sharon.
What I mean?
Yes, of course. Very mean.
Are you saying Sharon's average, or that she's mean?
We can. Hey, a joke on a joke. Multiplicative comedy goodness. Thank you.
Unsolicited fun. At least you don't have any college named after you. Oh, wait.
So the thing I didn't show you yet is this little argument. If you look at a of r minus h of z naught, then this is just straight up the integral. Well, first of all, the integral of h of just the constant is 2 pi times that, right? So if you divide by 2 pi, you just get back h. There's a stupid identity. H of z naught is equal to this integral. There should be an h of z naught in here. There's a typo. There's an h of z naught in here. Sorry about that, which is obvious from over here. But anyway, the point is, you can lump this constant into the. Basically, it's funny. It's just a quirk of this particular integration domain. You can pull a constant inside the integration essentially. So this becomes that integral. But then the modulus is this the, oh, it's real valued. So this is just the absolute value of an integral. The absolute value of an integral is less than or equal to the integral of the absolute value. That's calc 2, right? To prove that the modulus is less than or equal, I mean, that's something we haven't proved yet, and we will another day, I think. But certainly true for absolute value, and there it is. And, well, okay, so once you have that, as r goes to 0, you get a sub r going to h of z naught, because this becomes, as r goes to 0, this shrinks to h of z naught minus h of z naught, which is just 0, and integrate 0, you get 0, right? So the point is that the average value is, the average value function is continuous, and as r goes to 0, you get h of z naught. So that shows then that the constant over here we found, if you just let r goes to 0, you find out that the constant has to be exactly h of z, well, in this case, u of z naught in my current notation, which is the theorem we were trying to prove. Okay, so definition, we say a continuous real-valued function, h of z on a domain D has the mean value property if for each point z naught, the value h of z naught is the average of h of z over any small circle centered around z naught. So what we've proved in this section is that harmonic implies mean value property. So Michael, you'll ask me, is the converse true? Yes, but only in chapter 10.
Okay.
So, okay. It takes a while for us to get the converse to that. Now, section 3.5, I'm also covering today, believe it or not. So there's this strict maximum principle and strict maximum principle complex version. The arguments here are very beautiful, but they're topological in nature. Basically, the first argument's based on showing that this connected set is both open and closed. And so once you do that, it means that the set is either everything or what is it? It's either everything or nothing. And those two possibilities give you the result. So it's a connected continuity argument. This is just bootstrapping on that. It's easy to understand. I'll let you read it. The maximum principle, though, is really what I want to talk to you just a minute about. And here it is. Let h of z be a complex valued harmonic function on the bounded domain D, such that h continuously extends to the boundary of D. All right. Then, if the modulus of this function, this harmonic function, right? Oh, not harmonic, just complex valued. Oh yeah, harmonic. So if the modulus of the harmonic function is bounded on just the boundary, all right, then the modulus of the function is bounded throughout the domain. So basically what this says is a really, really powerful tool. It says that if you can bound something on the edge of a harmonic function, then whatever bound you find on the edge of the simply of the words on the domain, on the edge of the domain, if you can bound it on the edge, then the bound applies throughout the region. So this is a fantastic result, which I'll probably go through the proof like next class maybe. What I wanted to share with you guys, though, is just an indication of how to do one of your homework problems before I forget. So that oh, phooey, I'm out of time already. Well, I'll just tell you this. There's a homework problem you have about proving the fundamental theorem of algebra. If you want to get ahead of me, I'll try to talk about the start of next class, hopefully not too long. On page 131 of Churchill's complex analysis, he shows you how to, you can try to do this without his help, page 131, but if you have the modulus, if you have polynomial, all right, so this is an z to the n plus da-da-da-da, all right, and suppose that this is for z in some circle, it's in some circle, radius r. You can prove that the modulus of this is less than some constant times r to the n. That is not the easiest thing to prove carefully. I mean, intuitively it seems very believable, but to actually flesh that out, it takes some work. So I'll try to show you how we can do that start of next class. It's something technical you'll need in order to prove the fundamental theorem of algebra problem in your homework. So anyway, I will stop there. So.